All right, so here we are again with this equation that we cannot solve algebraically. We want to find where it equals 0, where this function f of x equals 0. We know from the graph it's got to exist. We see it on the graph. It goes from positive to negative. Intermediate value theorem, it's got to go through 0. How do we get there? Last time we looked at how you could use 2 points to kind of bracket the root and use this bisection method. Now I want to show you Newton's method, where you only need 1 point. So the way you use Newton's method, you start out by making an initial guess, right? Again, you do this based on a graph. Always look before you leap when you're finding roots so that you start out somewhere close to the point that you want. What you do is you start out at this point here. We're going to call this xg for x guess. I've drawn that up here where it's at the value fg for f at the guessing point. And what we're going to do, we're going to take this point. We're also going to look at the derivative at this point, because right at this point, there is a slope, an instantaneous slope at that point right there. We're going to take that slope, we're going to build a line out of it till we get down to 0 here. Get my line thick enough to show up on the camera. There we go. We're going to take this line, we're going to write it all the way down to 0. Right? Because what we're basically doing is saying, okay, I know the function here, and what if I knew the derivative? I could get the slope right there, ride this line all the way here. I'm going to end up a little bit closer to the root than I was before, hopefully. In the code, I'll show you how that can go awry. And we're going to make that our next guess. In other words, we're going to now ignore this point. We're going to make this our new guess and say, okay, where am I on this guess? Okay, I'm right here, so here's my fg now. So I overwrite the previous guess with this new guess. I'm going to do the same thing here. I'm going to take the derivative at this point, use that to make myself a line to end up here. Right? So I take this line, I ride it all the way up to the x-axis. Last time I wrote it down to the x-axis. Now I'm writing it up to the x-axis. That's a good sign because I'm going back and forth instead of marching off to infinity. Again, we'll see that go wrong in the code in a little bit. So I do the same thing here. I say, okay, this is my new guess value. So I can just ignore this part, override it with this value. I've got my new fg up here. Again, we'll do the same thing. We'll take the derivative here, get myself a line to come down here. Here's my new guess. And with each pass that I go through, I get closer to this root. So again, we'll replace the guess here. We'll come down to the actual function here. We'll go up this way. And now I'm getting really close to that root. So how many passes did that take me? That took me 1 line, 2 line, 3 line, 4 lines. It took me 4 passes to end up really close to the root there. Now, the way you end up with the equation for this line, the way you end up with what this next x is going to be, you have a few steps you need to complete. First, you need to take the derivative of this function that you're trying to get the root of. So in this case, that's going to be, what is that, negative sine of x minus 1. Derivative of cosine is negative sine, because anything that starts with a c gets a negative. Derivative of x is just 1. So I've got my function here. I've got my f prime here. Let's suppose I start out with my x that I'm guessing. Right? What I do to get the next one, my next guess is going to equal my previous guess minus a little correction factor. The way I get the correction factor is I take the function at x guess, right? Because I don't know x next yet. I only know x guess now. Sounded like Dr. Seuss there for a second. We're going to divide by f prime of x guess. And you say, why am I doing f over f prime? Well, think of it this way. This thing is your function, right? This thing is your y value. You're dividing that by delta y over delta x. So, and the mathematicians are going to rebel against me for this one. It's almost like the y's kind of cancel, right? So you've got your function and your function here. So you've got 1 over delta x. So this thing is like a delta x. So you've got an x next equals x guess minus delta x. So this is your correction factor here. So every time you do this, you evaluate this thing. This is your correction that you need to your previous guess. And you can kind of see it works out like a line. It's linear with this xg here. So you get all these tangent lines kind of zeroing you in on the root there.
So here's our Newton's method script. So here we need to define two functions. We need the function that we're interested in finding the root of. Here's x squared minus x like we had before. And then I need the derivative of it. Now, fortunately, derivatives are easy to calculate. Well, at least they're straightforward to calculate. You can always get a derivative. It's not like those pesky integrals where you can't always get one. But if you needed to do a numerical derivative, I suppose you could do the slope based on this thing instead. But you're better off putting the derivative in yourself here. And so we now just need a single point, right? So we don't need a left and right bound anymore. So we're going to ask the user for a guess, for an initial guess, as close to 0 as you can find. And then we're going to predict the next one just based on this formula we saw earlier. We're going to take x guess minus the function divided by its derivative. So we're just going to ride that line along until we get to the 0 point, to the intercept. So that's what we'll do down here. In this loop, we're going to keep going over and over again to get the next guess based on the previous one until we get a difference between the two results that's within our selected tolerance. And I've put in some extra animations in here. I want to show you what that looks like, because basically what we're going to do is we're going to see the line that we ride to get to that new point. Okay, so for our equation here, let's try going for, let's see, I know this root is at 1, so let's try guessing 1.5 and see how long it takes us to get there. So we're going to try a 1.5 as our guess. And now watch what happens. See, I'm following the line along here. I get to this point. I follow the line to get to this point. Follow the line to get to this point. You notice each of those steps is smaller each time until I arrive at x equals 1. And that took what? That took like 3-4 hops, was it? And so you can see that we're following the line segment there. Let's try that again, only this time let's go to the left of that point. Let's try a 0.6. All right, so we're going to hit OK. And now that's going to take me too far to the right, because my slope was very shallow here. But it quickly corrects itself and follows itself along here. You notice each time I'm taking a smaller step, because each time I'm getting a more accurate representation of the slope near the point that we're interested in here. All right, let's run that again. Now let's watch what happens. I went to 0.6. Let's watch what happens when we go to 0.4 now. So we're going to start over here. Here you notice the slope is going back this way. So now I end up on this side of the graph, and I start approaching. I start kind of spider climbing my way over here, and I end up at the 0th root. So the thing you have to look out for with Newton's method is these maxes and mins, because depending on which side of the maximum or the minimum that you end up on, you'll end up going to a different root, right? Let's see. Let's suppose I started way over to the left. Let's suppose I started at -1, so all the way over here. Let's watch what happens with my slope. I end up over here. I'm kind of like leapfrogging my way over here. I still end up at 0, hooray. The thing you want to be careful with, especially with is with these maxes and mins. What if I put in a 0.5? Because this thing has a slope of 0, so it's going to try leaping basically over infinitely big. And sure enough, I get a root of NaN. So the thing with Newton's method, it's a little bit more efficient than the bisection method. It doesn't require you to have 2 initial guesses, but you've still got to look before you leap. Literally, you're leaping in this case. Because if you start out at a max or a min, or if you end up at a max or a min, it's going to not go anywhere, right? You're going to end up with this NaN here. Let's see. Is there anything else? What happens if we start at the initial guess? Hopefully we end up there. Yeah, we do. Okay, good. All right, let's try another equation. Let's try something a little bit more challenging. Let's try our cosine of x minus x. So we'll click run. Again, we need to look before we leap. So for example, if I look before I leap and I start at, say, 0.5, I'm going to start at that blue dot, and that's odd. That shouldn't be happening. Oh, excuse me. Oops. Yeah, so when you change this, you also have to change this derivative. My bad. I make the mistakes so that you don't have to, right? So derivative equals our derivative cosine is negative sine. Derivative of x is 1. All right, let's try that again. There we go. Okay. I looked before I leapt. I just didn't look everywhere before I leapt. All right, so let's click on OK. So we get a segment going down here, then we need to go back up, and we end up finishing within a couple of jumps. That's pretty good. Now let's see, over here I don't quite have a, let's see, I do have a minimum over there, I suppose. Let's see what happens if I start out at negative, let's go negative 1.5. Let's live dangerously. Negative 1.5. The problem here is I've got very little slope to go on. All right, so I start over there. I end up way, way, way down at 500. I have way, way, way overshot. Now, it's still going back in the correct direction, it looks like. It's still heading back to where I need to go. But it's taking so much longer, right? The bisection method was so much more forgiving than this one is, because here I'm having to leap all the way around because of this enormous, the small slope that I chose that gave me this huge jump to begin with. Okay, here I'm getting back to my usual. Okay. That took way too long, right? All because I picked a spot that was too close to being flat. So you want to look before you leap. You want to pick a spot that's near the point that you're interested in, the root that you're interested in, and a spot that's got a good slope to it. Let's see. Let's try one more. Let's try the cosine squared minus x just for fun. Let's see, we'll do a cosine squared. Okay, I've got to do a power rule here, so I'll have 2 times cosine of x, and then I need the internal derivative is negative sine of x, so I can still keep that on there. Okay, let's see what happens here. I'll click run. Ooh, now this ought to be interesting. Okay, let's try this. My point that I'm interested in is right here. So ideally, I should pick maybe 0 to start with. There I go to 0. Okay, and here I'm going to kind of leapfrog around it a little bit. I jump up too high, and there I get my intercept there. All right, that took what, like 4 steps? I should have put in a counter for the steps. Now let's suppose I pick a spot that's got a good slope out here. All right, so let's call it negative 2, right? It's got a good slope. It'll jump down this way. All right, so it ends up over here. Uh-oh, now I'm at a point that doesn't have a good slope. And so even then, even though I didn't pick a bad spot to begin with, I ended up on a bad spot. And now I've got to overshoot my way back to the root. Again, overshooting. So anyway, I hope these are useful to you as you encounter these weird transcendental equations that you can hopefully use this. Do not do what I just did there. Here, let's get this back to a good setup here. Let's try 1. Yeah, 1. There we go. So anyway, I hope these are useful to you when you end up with a transcendental equation that you can't solve analytically. This can help you get to an answer there. Thank you so much for watching. I will see you next time. Bye-bye.